We are here for our third session of the day with Rob Zinkov. And Rob, you have you're going to talk on robust predictions and increased interoperability through domain-directed modeling. And as I look at your profile and seeing your great accomplishments at the University of Indiana, you're a research scientist, and you've built out Hakuru, the probabilistic programming language. Love to get your feedback. Love to get your story behind how did you get that started. That seems like the foundation, some of the things we're going to talk about today, but give us a little bit of that background before we get too deep into your discussion.
Sure. So I think the main context for that is, I think for a long while, many machine learning algorithms, like when you would sort of read machine learning papers, there would be this particular probabilistic model, and then there would be this very complicated inference algorithm to sort of get it working. And the inference algorithm always used all these little tricks, so it was always a little bit complicated to get it working. And this was like supposed to be very impressive, but it often meant in practice, I would read these very interesting papers, but it would sort of take me months to actually replicate them. And it kind of got frustrating after a while because you would have two ideas that are conceptually very similar, but you seem to not ever be able to reuse the work. So, you would see these articles for doing things like topic modeling. So it'd be different takes on topic modeling, different takes on, doing time series prediction. And you just you couldn't reuse these things. Like you would have to it was so cumbersome. You grab a topic modeling library, you grab a time series modeling library, and of course they can't work together. I mean, even in 2022, often a library for doing document modeling and time series modeling, they're not going to interoperate, or it'd be very surprising too. But I sort of discovered this language called JAGS, which showed that, actually, if you're willing to sacrifice a little bit of computational efficiency, you can actually get these models. You don't get to use all the tricks that the papers use, but you get to write the model and you get to use it for your task. And more importantly, because you have this little language, you get composability. So I was deeply captivated by this because that suddenly meant, okay, now I can mix and match models. I can really sort of kind of work on that. And I also sort of saw this is a real interesting opportunity because many of the reasons that these early systems are slow, that have computational inefficiencies, they're not fundamental barriers. They're almost all just things that with a little bit of attention and work, some software engineering, there should be no gap between whatever the fastest handwritten algorithm is and what comes out of these systems. And so that's motivated me to join with the former undergrad professor I had and develop the Hakuru project, which we worked on in Indiana for many years, to just show that, there's no reason that you couldn't make a system to let you write these fast inference algorithms, or get these fast inference algorithms while just being able to write your statistical model and not really focus on it. So that's sort of the context that I come in from.
I appreciate sharing that because I'd love to hear about innovation. And I know you work with Quansight, and they do a great job to incorporate, openness and the passion that you have for the things you found and continue to contribute. So let's talk a little bit about this domain-directed modeling, right, that you have created. And the problem you're solving is when you have a lot of data and you create your models, that's easy. Not easy, but it's easier to be able to create to analyze that data and get the results you want. But when you don't have a lot of data and you're trying to still deliver those business results, that's when things kind of get a little iffy. And I think that's what you're going to talk about here. So help us understand about domain direct modeling. What is it? Give us a little overview.
Right. Okay. Yes. So domain directed modeling is sort of like a massage term that I'm using, riffing off of this article from a little over 2 decades ago. So 2 decades ago, a statistician, Leo Bryman, wrote this article called the Statistical Modeling the Two Cultures. And so in this article, he basically goes, there's sort of, if you have sort of a data modeling task, there's sort of 2 ways you can kind of go about it. There's what he called the traditional statistical modeling way, where you develop a statistical model of your domain, and then sort of kind of follow it through, as we sort of expect sometimes from a lot of physical sciences. And then you have the algorithmic modeling approach, where you sort of just try to develop an algorithm that can explain the patterns in the data. And of course, the point of this article when it came out a few decades ago is that we've sort of over-focused on doing these traditional statistical modeling approaches, which I call which I'm calling domain-directed approaches, because when you write the model, it's very much motivated by your domain expertise, and more attention needs to be faced on the algorithmic modeling approach. I'm actually now arguing that it might actually be time to kind of go in the other direction, which is I think we've now actually kind of focused quite a bit on algorithmic modeling. And it might actually be worth it to kind of go back to domain-directed modeling, because it has very unique strengths. Namely, it can be much more robust. You can often use it when you have very little data or small amounts of data. It works better when your data is less uniform. And other sort of advantages we'll talk about shortly. So I actually think it's really worth it to sort of explore how to do domain-directed modeling. And the reason I think now particularly is a great time to get into it is that a lot of these tools and things like that I've explored. So like I've explored Hikaru, but I wasn't the only person doing this. Many people have sort of been exploring this, and we now have this sort of community of probabilistic programming people and these probabilistic programming systems. So there's actually now really nice software to do domain-directed modeling very effectively in a way that just didn't exist before.
And just on that one, what are the softwares that you suggest that they use, and when should you start using domain-directed modeling? When's a good point on your project to start doing?
Right. So it's such a challenging question because I love so many of these systems. But I think two of the systems that I think are probably two systems I think are kind of worth mentioning are there's of course Stan, which has sort of become very much the sort of one of the main modern systems. This is it's sort of its own little system with sort of access, library access from Python and R and a few other ones. And then there's PyMC. So these are both very deeply established projects. Each of them, I would say, is like has sort of close to a decade of active development. Looking further afield, I'm quite excited and contribute quite a bit to Bean Machine. So for people who use PyTorch, Bean Machine is written on top of the PyTorch ecosystem. So that lets you do this sort of domain-directed modeling using PyTorch and using a lot of the tooling around that, which if you're already using PyTorch and other parts of your business, it's sort of a very easy thing to explore. In terms of when you would do it, I think in many ways, it's a tool that I think you can often reach for a little earlier than you might something like scikit-learn, where you can often use a lot of these domain modeling tools for exploring the data. So you can sort of ask like, well, are there sort of different common attributes? You can sort of say like make a latent variable model and say, well, are there sort of common things involved here? So much in the way that you might do summary statistics, you can sort of, once you sort of move beyond basic summary statistics, you can start making very small statistical models and just see what inferences you get.
And can you give us some examples of where domain direct modeling shines? So as what your experience, or how can you illustrate that a little bit more for us?
Sure. So I think some of the places where I think it really shines is where you don't really have a lot of data, or your data is sort of very heterogeneous. So for example, and as an anecdote, a colleague told me about, they were testing the reliability of machine parts, and when they're doing the machining, it's very expensive, so they're getting like 5 or 6 data points. There's another example of Raveen Kumar, who used to work at SpaceX, would use Bayesian modeling for modeling what you should do for like rocket launches and things like that. There's not that many rocket launches. You don't get thousands of data points. It's not like other domains where you have millions of data points and they're highly regular. You get like, maybe a few dozen if you're lucky. You see it very much, in the sciences. You have things, for like astronomy, where you might use it for, say, exoplanet discovery. Again, like it's ones where it's not a lot of data, but it's ones where you really want to sort of really use your domain knowledge just to make the most of it. Which, of course, in all these domains, it's often things like physics and astronomy, for example.
Yeah, so the accuracy and interpretability of ML approaches are a major concern, specifically when it comes to like the healthcare industry. What are a few proven ways to improve the accuracy of the model, as you're talking about probabilistic programming and the use of it?
Sure. So there's always lots of different ways that you can go about it. All the ways that we use when we do regular machine learning algorithms still apply. If you can get better, if you get more high quality data, that can always help. There's always a bit of feature engineering you can always do, particularly in situations where you're trying to improve a probabilistic model. What often helps is it's looking at the data and looking at where are you not capturing a subtlety in the data. Sometimes you might, like, does your data have heavy tails? Are you actually capturing that in your model? Because if you're not, then you run into issues with robustness. There's a question of, does your model capture what all the data actually looks like, or is it sort of doing a bad job on an important subset of the data? And is it making assumptions that are reasonable? they're all like things of that sort that you can do. And what's nice about, of course, all these things is you can then go ahead and check and see, like, did it actually seem to do anything?
So, and as no, appreciate the response to that one. Now, as you're embarking on the journey to use one of these tools, which deterministic, probabilistic programming libraries work best with small and large data sets? What do you suggest that they use? How do you suggest they start getting started with this?
I think just what I said before. I think you can reach for something like Stan, PyMC, or Bean Machine. And I think they'll generally they're more or less interchangeable. I think which one you gravitate toward will depend on things that are less specific to the library and more your other business needs. If you're mostly a Python shop, maybe you don't want to be reaching for Stan, which seems to have better support on the R side. Or, if you're using a lot of PyTorch, you might reach for Bean Machine. And I think sort of in terms of the merits of the library itself, I think it's more about which ecosystem it sort of fits better into, because I think the capabilities in a lot of them, particularly for people who are starting out, I think are more or less interchangeable.
And as they go down this path, what are the most common errors you can potentially face during data modeling as you're working through this probabilistic programming?
I think a lot of the errors that people make they're kind of mundane in a lot of ways. A lot of it is just like people just use. So for a lot of these probabilistic models, they're often Bayesian models in particular. So you have to put priors on the latent variables that you care about, and people sometimes they, particularly if they have, this is one of those situations where like a little knowledge can be dangerous. If they're coming from a more frequentist statistical background, they'll sometimes make their priors overly broad, and this often leads to models that I think have bad geometry, to sort of use a term that sometimes used to kind of describe them. So you should often write priors that actually agree with what you think. So, if you're modeling the age of some of your customers, it's not clear to me that you should like have a model that puts a lot of weight on people who are 300 years old. If you're modeling pollution in the atmosphere, you probably don't want to put too much weight on pollution levels that won't exist on this planet for 1 billion years. So, and this is not meant to be glib or anything. It's that overly broad priors often just make these systems perform badly, and then people just think, oh, I guess my problem like isn't a fit for the system, and then you like significantly, we're talking about like they make this change, their model takes an hour to run, they put more reasonable prior, and it runs in a minute. Like, this is a very important sort of thing to do that can really affect the experience of using these systems.
Right. No, makes sense. So bias training, this is another question that came in here. Bias training data has a potential to cause not only unexpected drawbacks, but also perverse results by completely contradicting the goal of the business application during data modeling. How can we ensure balanced label representation in training data to avoid data-induced bias? So that was a question that came in here.
Right. I think a lot of the challenge there is you sort of need, I think, a source of truth to kind of keep you honest. So none of these methods, whether it be the methods I prefer or methods others use, can really do anything if the data itself is biased. They sort of assume the data is what it is. So I think often those things really require sort of external checks. So that really is trying, like, okay, like, is this thing, like, does this thing have the statistical properties that does the population in the data set have the same properties that we expect the population where the model will be deployed to have? Or, does this seem to have, like, worse performance on different subpopulations than we want to have for sort of different criteria? That really ends up being something that sort of ends up existing sort of almost like outside of the modeling process, sort of just like getting a sense of what the data you have is.
And no, thanks for answering that question. And one of the other questions that we have here that were submitted is, creating a model without understanding the business goals and missions can cause lots of problems. How can business ensure that they stay on track with their business goals, and the data modeler incorporates those into what they're doing?
That's a great question. Maybe that one was probably maybe I should have answered that one a little earlier. This is like how most data science projects fail, right? Like, you just not engage the relevant stakeholders early enough and forcefully enough. My experience has been, I think this is the experience of most people who work on data science tasks, is I think you just need regular communication with all relevant stakeholders. If you're making assumptions, people need to know about them early. You need to be managing expectations basically the entire time. And if you don't understand the business model, like, I think that's sort of like the number one priority to sort of correct before going off and making something that's ends up not being very helpful.
No, I appreciate that. Let's see, is there any other audience questions that people may have? So we have, thanks for sharing. We appreciate covering this topic with us. Now, you have a blog that goes into more detail about what we said that can be found on quansight.com. And we're more than happy we're going to post that link out to everybody so they can have that. And any other things you would like to share, Rob, or closing remarks? But we appreciate what you shared with us, and this is a very useful way to do data analysis, especially when you don't have all the data that you're looking for. And it's a good tool in many of our research, because many times we end up with less data than we wish we had.
There's always less data than you wish, right? Because the thing is, the ambition gets higher, right? Because it's like, well, if we have a lot of this data, well, now we can reach for things that are a little further out of reach. So it's like, well, we have all this data for language translation. Now, there's a temptation to reach for the less popular languages, the languages that have less speakers, maybe the endangered languages. There's always you can actually often always sort of subset your data until you suddenly don't have a lot of data anymore. And that subset, still begs very interesting questions. And it's often, I think often there's, because we know what to do when we have lots of data, we often sort of want to sort of dispel a lot of the interest and complexity in a data set to sort of answer the questions we think we can on the largest possible data set. So, things like local and regional variation suddenly falls to the wayside. Things about sort of more vulnerable populations falls to the wayside. Because again, these are things that you have less data for. But I think if you have tools if you have a nice broad range of tools, of which I consider domain-directed modeling just one that I think people would access, suddenly you can resist that temptation a little bit.
Yes, and I posted a link to your blog that you posted on Quansight.com. And Rob, thank you for your time today. We appreciate that, and for your insights to the community. And then coming up, we're going to take a short little break for a mic check, but we're going to come up to David Bunyatian. So appreciate that. Thanks once again, Rob.